Hello,
Hi,
how are you doing?
I'm fine, thanks. How are you?
Not too bad. I've been thinking about a Scottish village that was troubled by power cuts.
Oh, yeah.
So it happened a few months ago. So this village, it just got unexplained power cuts. No one was sure what was going on until someone actually went to look at the lines, and they discovered there was a kind of flock of starlings. They'd all land on the lines, push them down, and then so starlings would all fly away. The line would bounce up and down, smash into the other line, and that would cause a power cut.
Oh, I see.
And I always think we can model that using a harmonic oscillator.
Oh, yeah. Yeah.
Let me see if I can share a whiteboard so I can talk about it.
Excellent.
So can you see the whiteboard?
I can, yeah. Yeah.
Excellent.
And I can write on the whiteboard, although I can't say it. So these are power lines, the big power cables that stretch across.
That's right.
I don't know. Then would there be something like that?
That's like a very good drawing of a power cable.
And then what you're saying is that flocks of starlings land on the power cable.
Exactly.
So presumably we'll get a displacement then.
Mm-hmm.
Whoops, that's not as good a drawing. Something of that sort?
Exactly. Right up until they fly away.
This is while they're resting. So while they're resting on the line, we've got a displacement, say y, of the line.
Mm-hmm.
And then just to recap, you said then they fly away, the lines spring, bash into each other, and cause shortcuts. I see.
Power cuts.
And power cuts. Okay.
Maybe the starlings are taking a shortcut.
So how would we normally write this? So we could set it up like a mass spring system.
Exactly. I mean, really, we should model the whole cable. But I think a mass spring system kind of captures everything we need for this.
Right. Okay. So the standard diagrammatic representation where I might show a fixed point, a spring, and a mass attached.
Mm-hmm.
Obviously, we've got the mass, we've got a constant, the spring constant K to take into account. The mass, would you say the mass is the mass of the power line?
I would say so, yes.
Okay. Well, normally, if we wrote out our sister, or if we modelled that mathematically, we'd look at mass times acceleration. If we're using displacement in time, I ought to put dy dt squared. And that will be equal to the opposite force, the ky. Let me put it on the left-hand side as plus ky, equal to any external force that we've incorporated.
Sounds good. And then, of course, it's a second order equation, so you'd need some initial conditions as well.
Would. So initial condition wise, where would you go from here?
Well, maybe an initial displacement and an initial velocity.
Okay. So we can say time t equals 0. We need to find, or we need to consider a displacement and a velocity.
Sounds good. So I think the easiest way to model this is probably to imagine the moment just after all your starlings have flown away.
Ah.
So that way you can say the mass. You can say m is just the mass of the power line.
Mm-hmm. Right, okay. And instantaneously, that would give us the initial velocity is 0.
Exactly, because the line hasn't worked out the starlings have flown away yet. But then your initial y would be some kind of negative number, because it's the y is being displaced downwards by the weight of the starlings.
Okay, so would you like to introduce a constant for that? It's got, as you say, it's going to be negative. What shall we use?
Minus a was a good choice.
Minus a. Okay. And sorry, go ahead.
And then for your external forcing, I don't think we need anything there.
No. Okay, so if we say that RT is equal to 0.
Mm-hmm. Sounds good.
So how are we doing now? Well,
I guess we could write down a solution to this, couldn't we?
I think that looks looks like that's where we need to go next. So just, do you want to go ahead and do that?
Oop. Let's see if I can move the screen rather than drawing on it. Okay, so we've got. Oop. Well, let me rewrite that as d2y dt squared plus k over m y is 0. Now, it really upsets my students when I just write down the general solution to this, but I'm going to do it anyway.
I think it would upset many of us that you didn't first of all move that across before you went through, yeah.
Oh, let me write down the solution, then I'll explain where I pulled it from.
I think
so
that's reasonable.
General solution is A cos k over m times t plus B sine root k over mt. So there's a few different ways to see where this comes from. But one easy way is to think about the properties of sine and cos functions. So there's lots of different ways to think about sines and coses, but when I'm doing things involving differential equations, I always think about them as the functions which, when you differentiate them twice, gives you back minus the original function, multiplied by whatever constant you've got. So I think of cos and sine x as being like this. So let's see, so if I've got d by dt squared, of say cos omega t, that's going to give me minus omega squared cos omega t.
Mm-hmm.
And similarly, d by dt squared sine omega t, that's going to be minus omega squared in the same way as I sometimes think about the exponential function as being the function which, when I differentiate it, just gives me the original function back.
Mm-hmm. Yep. Okay, so I suppose now we've got this shorthand way, if you like, rather than saying let y equals e to the lambda t, etc., etc. We've got a nice shorthand way by inspecting the behavior of the functions, so we can put our general solution together using the two parts.
Because I think, what function will I differentiate it twice and add it to the original function multiplied by k over m? Gives me 0. And then I look at these two.
Mm-hmm.
I see, oh, that's going to happen when omega squared is k over m, or omega is root k over m.
Mm-hmm.
So then all I need to do is apply the initial conditions here. And I know that cos is flat when t is 0. So this has no derivative. So that's fine. But sine t does have a derivative. So I can use this boundary condition here to say that this term must be 0 or b equals 0. And then I can look at this. And because I know cos is 1 when t equals 0, that's going to tell me that my little a is going to be minus capital A. Oh, are you going to draw some diagrams to show that?
I'm just drawing cos t and sine t just to to hammer home your explanations.
Yeah, so cos t has a value of 1 and a gradient of 0 at t equals 0. And sine t has a gradient of 1 and a value of 0 at t equals 0. So one of the things that's useful to have is more than one way of looking at a function. So there's ways of looking at trigonometric functions which are useful when you're working out angles and geometries. But there's a totally different way of thinking about them that's useful when you're solving differential equations. So you think about the properties of their derivatives and what their values are when t equals 0. So putting all that together gives us that our y is minus a cos root k over m times t.
The minus a being our initial displacement of the wire when the Starlings were sat on it, of course.
Exactly.
Just from our boundary condition.
Yep. Oh, since you're drawing graphs, maybe you could draw me a graph of this one.
And we've got plus or minus a for our amplitude.
Mm-hmm.
And at t equals 0, we're at minus a.
Mm-hmm.
So I'm saying we're starting out here.
Mm-hmm.
Do we want a very precise sketch, or are we just going to...
I'm sure a rough sketch is fine. Yep, that would do.
Is that too rough? Are we decaying?
Not with the equation we've used.
We're not,
I mean,
are we?
in reality it will, but...
Yeah. So perhaps I should have been a bit less exact there. Kept the amplitude constant as I went along. So I tidy that up.
Yeah, I mean, I guess we could also talk about why we wouldn't bother with the decay unless it was very large. Because the reason we've been making a model like this is to work out, are the two wires likely to bash into each other? And that's probably going to happen in the first oscillation or not at all.
Yeah.
So unless the decay is so large that it significantly affects the amplitude in a single oscillation, we probably don't care too much about it. Because our model will only be valid until one wire bashes into another, after which very different physics will take over.
So what are our assumptions then, or what have we learned from modelling this? What factors were important in our model?
Well, there's one which is kind of explicit in the model, which is this A here. So this is basically roughly going to be the weight of all the Starlings give or take a factor of k, the spring constant. So the more Starlings you have on the line, the bigger this A is going to be. So if you wanted to avoid this happening, one way to do it would just have less Starlings on your line. So anything you could do to either make your flock of Starlings smaller or make less of them sit on the power line, that would reduce the amplitude. But there was another thing we put in the model, and that's kind of hidden inside your assumptions, where we said, you were going to say something there.
I was going to say, and that is that we've assumed that the Starlings have acted as we might if we pulled the wire down and released it. So we're making an assumption that they do leave instantaneously as a body rather than one at a time. Oh.
Exactly. So if they flew away more slowly, then you expect the wire to just creep up gradually over time rather than it leaping up. And there's a really interesting question, which is exactly how fast would they have to go to make this kind of leaping thing happen rather than this gradual decay? And you have to do some quite deep analysis of the equations to work that out. Although very roughly what it will turn out is that they have to, the time in which they leave the wire would have to be fast or small compared to the time of one period of the oscillation. So if you want to stop this happening, there's two ways you can go. So you can either have less Starlings on the line, or you can have them leave the line more slowly, rather than all in one great big flock. So let me stop sharing my screen. So what I really like about this is, it's a problem that's affecting a real world situation. But even with a very simple model, you can get a rough handle of what's going on.
That's excellent. It's really interesting. Thank you.
And it's fun to work through. On that note, let me stop recording.